Hey everybody, welcome back. We're going to be doing a lecture today on folds, faults, and joints. That might sound like something a little strange, but in geology it's actually a pretty exciting topic. In geology, folds, faults, and joints are the manner in which the Earth crumples and changes and deforms. I mean, we talked about plate tectonics at the very beginning of this lecture series, and you don't move entire continents around and sea floors don't spread apart without some things getting caught in the bind and getting torn apart and really messed with. So what we're actually seeing here, right here in this introductory photo, is kind of a good primer for what we're going to be talking about in this class, which is a series of folds, right? Here we see the rocks are actually folded. The rocks themselves are folded here, which means the crust is folded right here. It's pretty impressive. So here we have a fold going in this direction, coming back down and over here. And to show you how big they are, here's a couple of persons standing right in the center of this fold, something called the axis. We're going to talk about those here in a moment. And of course, this is overlooking the beach. So we're going to go ahead and talk about what it takes to actually bend rock, to fold it, to fault it, which means to break it. And joints are another form of breaking of the rock, but it has a different consequence. So let's go ahead and jump into this and see what we can put together, all right? I think you're going to enjoy this lecture. So what causes rock to deform? We don't normally think about rocks as deforming. Rocks are usually, solid as a rock kind of thing. It turns out rocks have different characteristics depending on the kinds of rocks. So we need to kind of learn about what it takes to make a rock change its shape, to do different things like fold, right? Like we see in this image here. What does it take to make that happen? So deformation is a general term that refers to all changes in the shape or position of a rock body in response to something called stress. We'll get into what stress is here in a moment. Rock or geologic structures are the features that result from forces, when we think about forces, this is mass times acceleration. These are forces in the Newtonian sense. Forces generated by the interactions of tectonic plates. The plates moving around, bumping into one another. Those rocks are colliding, and you can imagine the only thing that's going to fold something like a rock is going to be something else that is moving a rock. So it's going to be something very, very powerful. These include structures like folds, faults, and joints. Study of these deformational features is called structural geology. So somebody that goes out and studies faulting and the history of the Earth based upon the way it's deformed and crumpled, almost like a crime scene, they're referred to as structural geologists. And in fact, right here we can see an image of a fault. This is the Moab Fault. The Moab Fault is visible right along here. Let's see if you can follow the cursor up here. This is the Moab Fault as it's expressed on this cliff face. And you can tell it because here we see nice layers, nice bedding, that comes up over here and it stops. These layers should continue across, but they don't. And the fact that we have a completely different texture of sandstone on this side versus what's on this side shows you that there's a major structure in between, and this is a fault. And so the rocks are sliding past one another at this location. So studying this is called structural geology. Okay, now let's jump into what stress is. Stress is the force that deforms rocks. And in fact, it can deform anything, if provided that there's enough stress applied to it. So when stresses acting on a rock exceed its strength, so think about how strong a rock is, right? So if the stress is stronger than the strength, in other words, the ability of the rock to withstand that stress, the rock will deform by flowing, right? Almost kind of like the way a liquid will. It'll start to shift and flow and move and accommodate things. It'll fold, it'll start fracturing, or it will start to begin faulting. As we'll talk about what faulting is here in a little bit. The magnitude is a function of the the amount of force applied to a given area. So if you're putting a large amount of force on a small area, the type of structures that you're going to produce, whether it be a fracture or a tear or a fold or something like this, is going to be the result, right? So if you're putting a big amount of pressure or a big amount of stress on an area of sedimentary beds, the beds are more likely to crumple and fold. But if you put that type of stress on, say, a granite is more likely to fault. It's really hard to fold something like a granite because there's a huge amount of strength. All right, so stress applied uniformly in all directions is called confining pressure. So confining pressure. So this is when you have stress coming in all directions, uniformly in all directions. And so you find this type of stress, say down in the earth, in the mantle, you find it pretty routinely. You find it down in the core. So we have uniform confining pressure that is relatively the same in all directions. And so we could actually imagine this. Here we have a cube of material that's experiencing the exact same amount of confining stress, equal in all directions, right? So it's pushing in all directions and it's maintaining that shape. Stress, however, that is applied unequally in different directions is called differential stress. And there's different kinds of differential stress. So there's compressional stress. So compressional stress squeezes a rock and shortens a rock body. So here we see compressional stress, the arrow coming in this direction, an arrow coming in this direction. And of course, if you're going to be pressing on the sides, just like what we see here, that compression is going to have an effect on what's going on inside this block. Tensional stress pulls apart a rock until, a rock unit and lengthens it. So here we see tensional stress. On Earth, that tensional stress, that pulling apart, we see that actually at mid-ocean ridges. So this is where we see rocks that are being pulled apart from the central spreading center. And then the last one is shear stress. So shear stress produces a motion similar to slippage that occurs between individual playing cards, and I'll show you what that looks like here in a moment, when the top of the stack is moved relative to the bottom. So here we have shear stress. The top is moved in one direction, whereas the bottom is moved in a different direction. So almost like you're pushing it on the table. So that's what we mean by stress. Now, stress gives rise to strain. So they're very important. They're different terms. Strain is a change in shape caused by stress. So it's when you actually start to deform the object. So you're no longer stressing it. Like I can push on this table that this computer is on, well, unfortunately I don't have anything here to push against, but I can push against this table, and as long as I push on it, I'm applying stress. But if I take out a hammer and I hit it as hard as I possibly can, that stress will strain my table and it will break the table if I hit it hard enough. So strain is the deformation. It's the breaking of the rock, right? So strain is the change in shape of a rock caused by differential stress. Strained bodies lose their original configuration during deformation. So the idea is that as you're straining the body, it's taking on a new permanent shape. It's no longer having that old shape that it once had. And again, we use the analogy of a deck of cards. So here we see a shear ellipse that's actually drawn on the side of this deck of cards. So when you push on the side of it, you can use it to measure the amount of strain. We're not going to get into that in this class, but it's an important thing. It's called a strain ellipse. And it's pretty useful. In fact, it's extremely useful, especially in engineering applications. So how do rocks continue to deform? Well, there's three different ways that we can kind of think about rocks deforming. There's an elastic mode, a brittle, and a ductile deformation mode. So let's talk about these. Elastic deformation. So under elastic deformation, the rock returns to nearly its original size and shape when the stress is removed. So under elastic deformation, you put pressure or stress on an object, and even though it changes shape temporarily, when you let go, it goes back to its original shape. So imagine a sponge, right? If you had a sponge in your hand and you smash it down into a little ball, and then you let go of it, that sponge would probably unfold and almost take on exactly the shape that it had. And so that's what we mean by elastic deformation. It returns to its original shape. But if you exceed the strength of that material, you go into the next step. Once the elastic limit or the strength of rock is surpassed, it strains. In other words, it breaks by either bending, which is ductile deformation, or breaking, which is brittle deformation. And in this sense, plastically. So elastic means it can return. In plastic, it means it's broken, right? It's not going to return. There's something permanent in that change. And so we can imagine that when we look at this diagram over here. What we see over here is on the y-axis, the level of strain we're applying to an object, and the level of stress. And in the x-axis, we're showing the level of strain. So the amount of change that is happening in the shape of the object. And as we add stress, the degree of strain also goes up. So we see kind of this one-to-one response. And in the elastic region, as long as I don't get up into the plastic region where I start breaking things or folding things and changing its shape permanently, in other words, exceeding its strength, if I let go of it, it'll actually just return. As I remove that stress, it'll remove back to its strained position. Now, if I exceed the strength of the material and I get up into the plastic region, I apply so much stress to it, I actually start to fold it, bend it, break it, tear it, do any of those other objects, then it's not retrievable in its original shape. It'll start to plastically deform at that point. So you get into the plastic region once you go from elastic to the point where you actually physically fracture or break it. And once you physically fracture or break it, it's not able to be returned to its original shape. It will be permanently strained. So that would look like this. So imagine even if we got it up to all the way to the level of, we keep adding stress, 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 stress up into the plastic region. Once we get into the plastic region, we keep adding that stress. So eventually we'll fracture or break it or fault it, right? And once we've done that, we can let go of the pressure or the strain. I'm sorry, or the stress. And we can see what the permanent strain result is going to be. And on a diagram like this, all you do is you simply draw a parallel line over here from where the fracture is, and it looks like this. So the magnitude of permanent strain is represented here. The rock will not return to its original form once it exceeds the elastic region. So that's the important point we see here. Now, in terms of rock type, crystalline igneous rocks generally experience brittle deformation. In other words, it's really easy to get those into the plastic region. There's not a whole lot of bending of the rock. It doesn't really happen. Whereas sedimentary and metamorphic rocks with zones of weakness generally experience ductile deformation. In other words, they can fold, they can bend, they can flow, they can do things like this. They're not going to necessarily fracture or break like what you would see in an igneous rock, like a granite. Time is a big focus as well. So forces applied over a long period of time generally result in ductile deformation. So if you do something really fast, you're more likely to break it. If you do something really, really slow, in a period of time, maybe at the rate that, say, hair grows or something like this, you're more likely to get ductile deformation. Even in a granite, you can actually get ductile deformation. You can create these things called shear zones and things like this. So that's how rocks deform. Remember, you go from stress, you start to apply stress, the stress starts to strain the rock. And if you strain the rock into the plastic region, you will permanently strain that rock. And if you take it too far to the point where you break it, you're going to have this kind of permanent strain built into the new structure. And by the way, the earthquake mechanisms are very similar to this. We'll get into that when we get into earthquakes. All right, so let's talk about folds. So folds are super interesting, and they're really beautiful. They're kind of a showstopper when you see them out in nature. You just kind of stand in awe and you say, where in the world did that thing come from? This thing is amazing. One of the most famous folds is the King Oscar Fjord. It has a massive fold that you could see in it. It's in almost all the major geology textbooks that you see. And the reason why it's world class, look at this thing. These rocks here are just, there's huge layers, and they're just folded straight up and over. The amount of pressure, the amount of stress that is required to strain these rocks to form this kind of bending is incredible. So let's get into the text that we have over here. So during crustal deformation, rocks are often bent into a series of wave-like undulations called folds. So this is fold right here. Characteristics of folds. Most folds will result from compressional stresses that result in the shortening and thickening of the crust. So when we fold rocks, the way that it generally happens, and I would say almost always, the way that it happens is you're pushing in on something. There's compression that's happening, and effectively the rock layers, which were once flat, get crumpled up, they get bent up, and they have to find some space. And so they tend to stack almost like taking a bunch of spaghetti and pushing it all up, and it kind of piles up on top of itself. And it can do some really, really amazing things when you see them, especially in tall mountains. The outcrops can be beautiful, just like what we're seeing here. So that we do characterize folds into two separate, distinct types, anticlines and synclines. So anticlines are upfolded or arched sedimentary layers where the oldest strata are in the center. I always think of an anticline as with the letter A up here at the beginning. An anticline is this right here. It's where the rock layers, in this case, move up, they fold, and they come back down. This is called a kink fold right here, or a chevron fold. So here we see a chevron fold where the rocks move up and then they come down in an A form. So that A that we're seeing right here, and here's another one right here, that's an anticline. I always remember A is for anticline. And so when you see these out in nature, you know that you're looking at these. And so synclines are the other side, right? The synclines are downfolded or troughs of rock layers. So here's a syncline right here. Here's one of those troughs that we're seeing right here. And we can see that it's been downfolded in this direction. And I always remember a syncline because there's kind of a funny saying that I heard from a teacher that I had once, which is that you must always smile when you sin. So it's kind of funny. So here's a smiling rock, and therefore this must be the syncline that we're seeing here. So in this case, the youngest strata are in the center. So here's the anticline, and here's the syncline. And we're seeing both of these expressed in this outcrop. In fact, here's another syncline over here, and it looks like there's another anticline on the end over here. So depending on their orientation, anticlines can be described as symmetrical. In other words, everything is nice. Let's see if I can get this. A nice symmetrical mirror image of each other. Or they could be asymmetrical, where the limbs of the folds are not identical. They could be overturned, right? They could be like this. So this is where one or both limbs are tilted beyond vertical, or they could be plunging, right? So one way that we could think of plunging, so let me take this piece of paper that I have here. So here we're folding, here we're looking down in this case, a syncline. A plunging syncline is one where the axis, which is the spine of the syncline, I'm sorry, I keep calling it syncline, the anticline is pointed, say, down or up, okay? So that's a plunging fold in that case. So the axis goes into the ground or up out of the ground, one or the other. All right, so let's get a little diagram of what kind of a mountain belt would look like, or a series of folds would look like, all crumpled together. This is a real simple one, showing all the different features. And this is, again, another really, really common image that we see in textbooks and all over the internet. So it's a classic image, so we're going to work from it a little bit. Here we see an anticline. There's that A structure. Here's the syncline, where it goes into that trough. There's that smile that I was talking about earlier. Here's another anticline, but you'll notice that this one here has a little different shape. So let's look at the shape of this one, and that's described as a symmetrical fold. We just described those. Here we see one limb, so these are referred to as limbs. So we have a limb of the fold right here, and a limb of the fold right here, and they're roughly symmetrical about something called the axis, or the axial plane. The axial plane is the folding of rocks going right down the spine of this right here. So we would assume that we have a big anticline right here, and then a syncline right here in the middle as well. And so here's another axis, in this case for the syncline. Here's an axial plane, in this case for the asymmetric fold. Now notice that the axial plane here is straight up and down, but here it's tilted, right? Let's see if I can do it in the image properly, because it's a mirror image that I'm looking at in the computer while I record this. It's going to be in the other direction. So it's going to be like this. And so here we have an axial plane that's tilted, and the consequence is that the limbs are now asymmetrical. And then if we continue to take it further, then what we'll notice is we get an overturned fold. So this is an overturned anticline right here. The axial plane is starting to move to the point where it's flat. And so once we get to the point where it's getting pretty flat, in order for this fold to work, that limb is coming over. It's obviously asymmetrical, but it's so asymmetrical that this limb and this limb are both tilting in the same direction, or as the term we use in geology is it's dipping in the same direction. So here we have a dip going in this direction. In other words, any water that's on this surface is going to go down this way, and then any water that's on this surface is also going to go the same direction. So it's overturned, and it creates a nice S, or reverse S in this case, on the fold. So that's what we mean by a symmetrical fold, an asymmetrical fold, and an overturned fold. All right, so let's take a moment to look at the anatomy of folds in real life. So here's some great chevron folds that are a classic image that we see, again, all over the internet. These are in Ireland, and I'm going to take a quick moment and switch over to another program, and we're going to talk about the anatomy of these folds. So hang on while we make that change. All right, now we've got the image from Ireland loaded up into a new application, so we're able to draw on the picture and do a little discussion about what's going on here. Let's talk about the anatomy of these folds here, or actually let's talk about the anatomy of the outcrop. So the bottom of the outcrop is located down over here, and we can see that it's actually right next to the water. So we're not going to worry about the debris down here on the bottom or the beach material. But we do have to notice that there's something up here on the top, that there's a totally different unit here than what we see below it. This stuff up here is not folded. It is effectively loose or relatively unconsolidated sediments up here at the top. It's a depositional deposit, or it's a deposit that is not solidified yet. In fact, there's soil, there's gravel, and this over time could eventually become a rock, but it isn't one now. And it's certainly not related to what's below it in terms of its history. It just happens to be sitting on top of it. And this flat surface that exists between the two of them is referred to as an angular unconformity because these rocks are coming up to the base of it in the form of an angle, right? It's not coming straight on, it's coming off at an angle. So we're going to go ahead and draw a line that separates these two. Hopefully the pen works. Ah, it's working. Okay, so we've got a pen working here, so let's draw that line in there. And it separates the top material from the stuff at the bottom. This is an angular unconformity. We'll just mention that right now. This is an angular unconformity. All right, so there's our angular unconformity, and we're going to be focusing on the rocks below the angular unconformity. And of course, if you recall from the lecture on geologic time, an angular unconformity suggests that there's a huge amount of time between these two events, right? This stuff is not solidified, it's not folded, it's not faulted, it's not altered. This stuff down here is folded, it's solidified. It's a completely different geologic history. It's considerably older. So this line that we've drawn on here is a considerably older structure. So what we want to do now is we want to follow, say, one of the beds and follow it through this whole structure here because it gets a little confusing unless you get some type of guideline. So I'm going to go ahead and put it in, I don't know, let's put it in, we'll put it in lime green for fun. And the best one to follow, it turns out, is this one over here. And so we'll draw a nice line in lime green. Follows that one layer, it comes up, it hits the angular unconformity, and then it kind of disappears. It turns out it's also this large one over here. So it reappears over here, takes that turn, comes over here to this elbow, takes another turn, and at that point it goes underneath the image of me here on the screen. So that's where it's at right now. Now we can infer something really interesting about where it goes up here, or where it was at one point when it was folded, because these rock layers below it are not eroded off. So here we see this darker one right here. It's making this shape, and here we can clearly see it looks like an M. The unit right below it is touching right here. It's making an M. So it looks like this thing here would have followed exactly along the same path. And we'll dash that in there. So we actually have what it was looking like. So that's probably one of the best ones to look at. And we could do it to several of them, but this is actually going to be sufficient to be able to demonstrate what our interest is in this. So at this point, now we have one layer in here. Let's switch to red. So we'll go to red. And what we want to do is we want to look for where the folds are. And the folds are pretty obvious. What we see here is at this point there's an inflection point where it changes direction. Here's another one that changes direction. And so it turns out we'll follow one fold axis at a time. We'll start right, let's start it right here on this one. This one's a nice one. So right here we see an inflection point. I'll draw a dot. And then it turns out the rock layers underneath it are also have these inflection points. Here's one right here. Here's one right here. These points, right, where the rocks are folded into a nice kink. And then it seems to be doing the same thing up over here. Another one up over here, and then right up over here. And then we could draw a line effectively connecting the dots. And what we're doing here is we are drawing in the fold axis. So there's the fold axis. And the fold axis here is going all the way through the rock, all the way down, presumably below the beach. And then it comes up above to the angular unconformity. The angular unconformity cuts it off. Are there any more fold axes in here? Yeah, there's actually several of them in here. There's one really big, obvious one right here. So here we've got a kink right there, one here, one here. We could just follow this straight down. It goes right down here into the bottom here, and we could draw another axis. We see another one right here. I'm not even going to bother drawing it. It gets pretty obvious right through here. And then we'll actually draw it all the way up to the dashed line up over there. So this presumably comes down here. Here's another one that gets a little hard to detect where it's at over here. It seems to be kind of fading out, but it looks like it does this, and then we kind of lose it, so we'll put a question mark. That's a standard geologic parlance. You know, it just means it goes down there and it either ends or we just can't track it. It's very likely the rocks continue to be folded, but we're not there, so we can't see it. And then we have another fold right over here, and this one seems to be coming in just like this. Okay, and so these are all these different axes. And when we look at these things, we can tell right away we have axes of different kinds of folds. So here's an axis, in this case, for a anticline. So this is an anticline. Axis. But it's not a symmetrical one, right? These limbs are not equal on both sides. This one here goes off in this direction. We'll put an arrow. But this one here goes off kind of in this direction here. And they're both going the same direction, even though they're both kind of going kind of in this direction here. The fact that they're both going in the same direction shows that this is, in fact, not just an anticline, but it's an overturned anticline. So this is overturned. And of course, when you think about an anticline, you know, you should think about this is the A in the anticline, and if you have water running off one side and a symmetric one, it should go off on the other side too, equally. This one here, that's not the case, right? It's completely overturned. The axis is pretty flat. It's not straight up and down, it's a flat axis. Now let's move over to the next fold axis next to it. This one here is not an anticline, this is a syncline. And this is in fact an overturned syncline right here. So here we see it's hitting this one here. If we were to drill straight down and keep going straight through this rock here, I'm trying to do this as straight as I possibly can. But we hit the structures twice. So this limb here is overturned as well, and so this is a syncline axis. Here's an anticline. Put A and T, the dot. What do we have here? This is a little syncline. Here's an anticline, and we'll notice that they go in crumpled sets. So these rocks get into this area here, and things start going crazy really quickly, right? There's a lot of crumpling, but you can actually map out these axes, and they're all slightly, they're certainly asymmetrical. They're not symmetrical, and we can see these limbs are not equal here. They're not equal here. They're not equal here, right? They're not, they don't look like a nice symmetrical fold like what you would expect. So these are largely overturned with the exception of this one, and, well, no, this one is overturned. These two are not, don't appear to be completely overturned, though there's some potential for it right up in here. These are standard anticline, syncline sets that we see in nature. And this is a beautiful exposure of them underneath a wonderful angular unconformity in Ireland. So I just wanted to take some time to kind of go over the anatomy of these things. It's easy to actually start with something a little more complicated, because if you understand the complicated one, then the simple ones become very obvious. All right, so let's go back to our other program and pick up where we left off. So here's an outcrop of an anticline. I believe this is a photo taken in France, if I can recall. This is a path that leads up to a cave, and the cave is located right in the axis of an anticline. You can see that there's a nice, in this case, it's a symmetrical anticline, or a fairly symmetrical one. There's a lot of erosion that's cleared off a lot of the rock over here to the side. But effectively, we're seeing a classic anticline structure. Upwarping in the center, symmetrical limbs on the sides with an axis that goes right down the spine of that fold. And in contrast with that, we see a syncline here. So this is an outcrop of a syncline. The syncline goes down here. Here's this. Roughly, this is where the axis is going to be located right here. And here we can see it's a syncline. It's smiling at you, right? You can't sin without a smile. So that's how I always remember a syncline. Okay, so it turns out that you can also get other ductile features, structural features like domes and basins. And they're really actually pretty simple. They're really modifications of synclines and anticlines. A dome is really an anticline in 360 degrees. So if we think about an upwarp, just like we see in an anticline, a dome is just a 360 degree upwarp. And so the consequence of that is you get these circular features. They're relatively circular. In nature, they frequently are actually more oval than anything, but they can be relatively circular. And so the consequence of the upwarping is that as you warp things up, the stuff that's down lower, below those rocks, get pushed up higher, and therefore they tend to get exposed in the center. And so the oldest rocks tend to be at the center, and the youngest ones are on the outer portion. And so this is a cross-section of what a dome would look like. In contrast, a basin would be the exact opposite. In this case, the older rocks would be forming kind of the basin, almost like the bowl, and then all the younger rocks would be the ones in the center because they would be downdropped, and when you went to erode everything flat, those would be the ones exposed. And so here we see that in cross-section, where the upper layers are concentrated in the middle, whereas the older layers are concentrated in their exposure on the outside. Great example of this for a dome would be the Black Hills of South Dakota. This is a great image. It's a very famous image that you can find on the internet of the Black Hills. This was drawn a long time ago, but somebody actually posted this over here where they colorized it. And I really enjoy this. It's much easier to explain things. So what we see over here in these colors is that we have a limestone plateau. These are the sedimentary rocks that were draping the landscape at the time, a long time ago. And then there was an upwarp. The dome was actually uplifted in 360 degrees. And what we see is the central crystalline area, the granites and the schists. We also see those labeled over here. Those were uplifted into the core. And so that becomes the Black Hills of South Dakota, the famous Black Hills of South Dakota. These central crystalline rocks, which are the oldest rocks, are really at the center and actually at the high point of the structure. Whereas the softer, weaker rock, but it's also much younger, is around the outer portion. So this is a really great place to go and visit. In contrast with that is the Michigan Basin. And the Michigan Basin is a downwarped basin. In terms of the basement geology, it's pretty obvious that it is when we look at a cross-section. So here's Michigan right here. When we do the cross-section of Michigan, it looks like a bowl, right? And in fact, you'll see that it's relatively circular in this location here. And so this basin, which has the youngest rocks in the center and the oldest rocks over here on the outside, Silurian rocks going all the way around, this is a classic basin structure that we would see, and this is caused by downwarp right here at the center. This is a really, really great basin. It's also much larger than the Black Hills. These basins can be massive. I mean, the size of an entire state, right? Whereas the Black Hills are not quite the size of an entire state. They're still majestic features, but not quite like what we're seeing in terms of the Michigan Basin. All right, the last ductile structure that we'd want to talk about in this lecture is going to be monoclines. Monoclines are amazing, and they're beautiful, and they can be extremely large. One of the most famous ones is the East Kaibab monocline. You can see it when you fly over it. Every single time I fly across country, I fly over it. I try to get a picture of it. I've never gotten a good, effective picture of it. But this is what a monocline is. It's a large step-like fold in otherwise horizontal sedimentary strata. So these are rocks. These are sedimentary rocks that folded ductily that are just draped down. So the rocks over here, or I should say the basement rocks over here, were either downdropped or the rocks over here were uplifted, one or the other. But the rocks that were sitting on top didn't shift, or I shouldn't say they didn't shift, they didn't break. Instead, what they did was they ductily deformed. In other words, they draped over almost like a blanket across this zone of deformation. And so here we see a cross-section of what we would expect to see in a typical monocline, which is this block down here moved down, or this one moved up in relationship to a fault. So this would be what a fault would look like in a cross-section. But the sedimentary layers above it are just draped over. They don't break, they just simply fold along as the basement moves. All right, so now we've finished our discussion on ductile folding or ductile deformation of rocks. It turns out that a lot of the deformation that we see on the Earth also is accommodated in a completely different way, to the point where we actually break the rocks. And that means we got to talk about faults and joints. And so faults and joints are rock structures formed by brittle deformation. In other words, the breakage, the snapping, the crunching of rocks, rather than just the folding or the ductile movement or the flowing of rocks. So faults are planar features, or I'm sorry, planar fractures in rocks along which displacement has occurred. So imagine, a planar feature. It's a piece of, something flat, and it's moving relative to another side, right? So my hands right now are faulting, right, because they're moving. So let's see here if I can get it in the image here. So when I go like this, just like that, that's going to be a fault structure, right? Because there's displacement. One hand is moved relative to the other. Joints are a little different. Joints are planar features, just like faults, in rocks along which there is little or no displacement. In other words, it's just a break. So here we see joints. These are breaks that we see in rocks. And we'll notice that the rocks haven't moved. They haven't gone anywhere. There's nothing offset. There's nothing changed. But we see these, what we call sets of joints in here, these fractures in here that are pretty regular. They almost form a pattern. We're going to get into that a little bit later after we talk about faults. Faults show displacement. These are faults in here. So here we see this red layer as it comes into these rocks. There's a fault zone here. And what's happening is this fault zone is ripping this rock into little pieces, and it's offsetting the rock layer. So this rock layer used to be matching here, because here we got red, white, red, red, white, red, red, white, red. We can see it's all the same unit coming through here, but this fault has offset it. They've moved it. So that's what we mean by a fault, something that is offsetting a brittle fracture or brittle structure. So we need to kind of wrap our minds around some of the anatomy of these faults. Just like we spent a little time studying folds and synclines and anticlines, faults have their own anatomy that we have to be aware of and how it's all put together. And so the first group that we want to talk about, it turns out there's two different kinds of faults. There's dip-slip faults, and then there's strike-slip faults. The dip-slip faults are faults that occur when there's movement that is parallel to the inclination of the fault. In other words, here's a fault in this diagram over here. We'll get into what all this means here. But here's this fault. It's the structure that's between the pink and the brown. And this is the fault right here. And effectively, what a dip-slip fault means is that this here, this direction that it's inclined, we call that the dip, is also the direction that the fault is going to move. It's either going to go down or up, but it's going to be in that plane, moving along that structure, either up or down. That's called dip-slip. So let's talk about the anatomy of this. The hanging wall is the rock surface above the fault. And so when we think of a hanging wall, we're talking about this here. So the fault is inclined right here. There's a hanging wall block. And where this comes from, as it's old mining terminology, in fact. So it was pretty common back in the day for miners to go into a fault zone, dip-slip faults especially, and mine valuable ore deposits that were deposited along faults. And so what they would do is they would put a mine shaft right along that fault, and they would basically follow the fault and try to mine out as much of the ore as they possibly could. And the wall that was above them, this one here, is called the hanging wall because they could hang their lamp off the top of it. So it's called the hanging wall. And their feet would be down here at the bottom of the mine. And so because their feet were on this bottom part over here, it's referred to as the footwall. So here's the footwall block, and here's the hanging wall block. So the hanging wall is the top, the footwall is the one that's on the bottom, if you were to stand inside the mine. And so that's a terminology that still carries over to this very day. It's used by scientists. And probably will be used for scientists for a very, very, very long time. So it's important terminology to know. So the footwall is the rock surface below the fault. So here's the fault, this is the rock below, here's the rock above. All right, so let's talk about dip-slip faults in terms of the way that they look and they move. So here we have a great diagram. This is another dip-slip fault. The hanging wall in this case is moving down. The footwall relative to the hanging wall is moving up, right? So there's sliding in this direction. So what we see here is the vertical displacement along the fault produces long, low cliffs called fault scarps. So the scarp is right here, right? So this surface here was matched up with this surface, and it creates a fault scarp after the earthquake happens or after the motion on the fault happens. We see these things after earthquakes frequently. This is one, I believe this is in New Zealand, if memory serves. And this is a fault scarp that is formed because this area here moved down from the landscape that it was over here. So this is a down-dropped landscape. In fact, there's a lot of people up here on this cliff that's checking out this amazing fault structure that formed. Another thing that frequently happens is the formation of sag ponds, which we'll be discussing a little bit later. But these are ponds that form along faults, especially active faults. And so here we see a sag pond that is formed at the along the this fault in this little gully over here. So we'll get into that a little bit later on. So there's two important classifications of dip-slip faults. The most important one to learn, because everything else is kind of derived from it, is the normal fault. And so it's called normal because it's normal. Normal faults are characterized by the hanging wall moving down relative to the footwall. So here we see a normal fault. This is a rock layer that comes over here. This yellow part right here is called fault gouge. We'll get into that a little bit later, but that's the fault itself. That's the fault actually ripping through this very, very soft. It looks like it's going to be, in this case, shales. And then there's a sandstone unit or some thicker unit that we see over here that is a little more robust, and it's offset from here to here. So this unit here has dropped down, and that's what we call a normal fault. So this hanging wall is dropping down relative to the footwall over here. And so we see this young geologist that is posing next to this active fault, or this presumably recently active fault. And it's associated with tensional stress that pull rocks apart. So the way that you get this thing to fall down is you pull in that direction and you pull in that direction. And in doing so, as you pull things apart, one side tends to drape down and fall down relative to the other as you pull things apart. So you get a lot of normal faulting when that happens. And here we see a nice block diagram showing what a fault block with a footwall block and a hanging wall block drop down, what that scarp would look like in nature after erosion. All right, so you can get very, very small ones, like what we're seeing here. This is a relatively small normal fault. Relatively, it's an extremely small normal fault. It's still a beautiful one, but it's very small. Or you can get really, really, really large structures. And these structures can be as large as entire provinces of continents. So larger scale normal faults are associated with fault block mountains. And a great example of this is the Basin Range province of the United States. This stuff extends all the way from Colorado all the way to Eastern California. It's a giant structure. And what this is effectively is you have these uplifted blocks that are called horsts. That's the structure right here. And down drop blocks that are called gravens. So when we come over here and we look, unfortunately, let's see if I can, you can see right here. This is a horst right here, and the word graben is right here. So here we have a horst. That's these high points over here. Here's a horst, and then the word graben is kind of underneath my picture. Unfortunately, I wish I could remove myself and show you that. But the faults are bounded on both sides here. And so these are normal faults that are dropping down this graben. And you can also get another kind of structure where you get a horst, and on the other side you get something called a half graben, where it's not dropping down on both sides, where you have two horsts and the whole center part is falling down or dropping down as the horsts are separating apart. You can get a half graben where, as things separate apart, what happens is one basement rock, or some of the basement rocks slide down and rotate out of position. And so that's called a half graben when that happens. That's what we're seeing here. Half grabens usually sit on the back of something called detachment faults. Detachment faults are massive faults. And anybody that studies structural geology, they spend quite a bit of time learning about detachment faults and the effect that they have on entire regions. So a detachment fault effectively is a major fault that dives down into the crust of the earth. It's separating and breaking things apart, intentional stress. And what it does is it comes down and it intersects between the boundary between ductile and brittle rock units, and then everything else is basically taking a right on the top of it. So here we have these half grabens that are rotating as this detachment fault slides these rocks in this direction and pulls them off. So it's almost separating and removing. And what that does is it pushes up one corner. You get a half graben, or right here, and a downwarped basin. And then here we have another downwarped basin. So these are half grabens that we see in here. It can get really, really interesting. It can get semi-complicated, but it's really, don't think about it too much. Don't get bogged down into the details. A graben is just where you have faults on both sides. The horse are these high points in the middle, on the sides, the graben's in the middle, and as the horse separate apart, the graben drops down. For the detachment fault, as everything is pulled apart, almost like you're pulling apart a Japanese parasol or a fan, right? That you can imagine seeing in any type of decorating shop. As you separate those things open, these images that we're seeing here, let's see if I can get my pen to show up here, these things here also open up. So it's a very similar thing that you would see. All right, so that's a lot. Normal faults are extremely important. But now we got to get into their very close kind of their sister system, which is the reverse fault. So if you have normal, that means you also are going to have a reverse. So reverse faults are characterized by the hanging wall moving up, not down, but up. So normal faults is down, reverse fault is up, relative to the footwall. And this is associated with compressional stress as the crust shortens. So instead of pulling the crust apart, which makes normal faults, this is about pushing them together. So if it doesn't form folds, you can actually fracture the rock, and what will happen is the rock starts to try to stack on top of itself to try to make more space. And so here we see compressional stress in a block, and so this is being pushed in this direction, this is being pushed in this direction. Here we see that reverse motion where the hanging wall block is being pushed up above the footwall block. And so this is what we see here. This is a reverse fault. Here's the fault right here. And there used to be, obviously, something pushing over in this direction, and it was pushing these rocks this way, but it's now been eroded off. But you can still see that these layers here match to these layers, and they've been pushed up along that fault, that reverse fault. So this is another famous photograph of a reverse fault. All right, so there's also a special case of a reverse fault, and these are really impressive. They're almost kind of the same way that detachment faults can be very large and have a massive influence on an entire region. It turns out that there's a reverse fault equivalent that can do the same thing. So, and it's referred to as a thrust fault. So thrust faults are a form of reverse fault. These are thrust faults have an angle of less than 45 degrees. So this angle that we see here between the hanging wall block and the footwall block is shallow. It's pretty flat. And the consequence of this is that you can push things like a bulldozer a really long distance in that way. Rather than just try to ramp it up into the sky, you can push it along the land surface. And so these thrust faults can move a tremendous amount of material very long distances. Great example of this would be Glacier National Park. In Glacier National Park, there's something called the Lewis thrust, and it's very well documented. Anybody that goes through the area can very rapidly identify it if they know something about what we call the stratigraphy. It's the order in which the rocks exist. So the idea of the Lewis thrust is that you have these Precambrian rocks down low, which are the oldest rocks in the area, and then you have these Cretaceous rocks, which are much, much younger. That's about the age of Tyrannosaurus rex, for example. And what you see is if you put stress, you start pushing in one direction, a fault will develop. Almost the same way as a detachment fault kind of comes up like this, except in this case, instead of pulling, it's pushing. And what will happen is you'll start to bulge it up. These Precambrian rocks will start getting ramped up over the land surface. They'll sit on top of the Cretaceous rocks, which are much younger. And eventually you'll get a whole mountain range, Glacier National Park in this case. And this fault would have reached all the way over and hit something called Chief Mountain. This line here and this line match. Since then, there's been a lot of erosion, so Chief Mountain is now by itself. I'll show you what that looks like here in the next slide. It's here. And so here's the Lewis Thrust Fault here, and it connects to the mountains behind it. Here we see those Precambrian limestones, those really, really, really ancient limestones sitting on top of Cretaceous sandstones and shales, which are much, much younger. This is an incredible thing to see for geologists, and this is the famous Lewis Thrust Fault at Chief Mountain at Glacier National Park. All right, so we finished up our discussion on dip-slip faults. These are the faults that if you have a scarp, a fault, where the rocks are moving up or they're moving down. If they're moving down, it's normal. If they're moving up, it's reverse. That's the system. In this case, we're talking about a different kind of fault. These are strike-slip faults, not dip-slip faults. So strike-slip faults are characterized by placement that is horizontal and parallel to the strike of the fault. In other words, the fault is sitting like this. Instead of things moving up or down, it's going in or out. It's either coming, in the case of the camera, it's either coming towards you or away from you, right? That's called going up and down the strike of the fault. So that there are types of strike-slip faults. There's two that you need to be aware of. There's the left lateral and the right lateral. So the right lateral is as you face the fault. So here's a right lateral. So let's say that you're standing right here. The opposite side of the fault moves to the right. So if you're standing right here and there's an earthquake, everything on the other side of the fault moves to the right. And that's what we're seeing here. This block is moved off to the right. And if you're on this side and you're looking across, it's also moved off to the right. They're both to the right. So it's called a right lateral fault. So it doesn't switch depending upon which side you are. So everything moves off to the right no matter which side of that fault you're on. In a left lateral fault, you want to look across and see what the other side of the fault is doing. In this case, it's going to the left. So they call it a left lateral fault. Same thing over here. If you're over here and you look across, everything's going to the left. That's a left lateral fault. And I have a little note in here. The key is to notice which direction the other side of the fault moved. So you want to make sure that you keep that in your mind when you're trying to figure out if you're looking at a left lateral or a right lateral strike-slip fault. And remember, strike-slip faults in general do not move up or down. There can be slight problems with faults moving, and it might push something up or pull something down. But overwhelmingly, the motion is side to side, right along the land surface. So there's some important common features along strike-slip faults that are extremely important for humans to know, other than the fact that they generate earthquakes. Those features include sag ponds. Sag ponds, as we've already described, these things can also occur on dip-slip faults. Linear valleys. So here we have a sag pond. Here's a linear valley right down the middle. Right here, we've got hills on the sides, and then we have offset drainages. So drainages will hit it and they'll be deflected, they'll move. And offset rocks and soils. Rocks that should be right next to each other are now very long distance away from each other. So it's a big difference between the two of them. This is all expressed along the San Andreas Fault. This is a great example of this. San Andreas Fault is located right here. Here's our linear valley right through the middle. I mean, classic linear valley. Offset drainages. These drainages here are all being offset and captured across the fault and being deflected and moved. We don't actually see any sag ponds along here, but trust me, there's some very famous sag ponds along the San Andreas Fault. And there's huge offsets of the rocks, tens of miles, sometimes further than that, depending on how old the rocks are. So the San Andreas Fault is a monster fault that is moving a huge amount of material in a direction that we would call right lateral. So if you're over here, everything on this side is moving this direction. If you're over here, everything is moving in this direction. So again, right lateral strike-slip fault. The great thing about strike-slip faults and their role in plate tectonics is that they effectively form the major transform fault unit. So strike-slip faults can also form transform faults. So large strike-slip faults that cut through the crust to accommodate plate motion are called transform faults, such as California San Andreas Fault. So here we see the Pacific plate moving, in this case, to the northwest. The relative motion of the North American plate is to the southeast. So the San Andreas Fault is just basically the barrier between the two. And effectively, as this moves, Los Angeles is moving up to the northwest, The rocks over here in the eastern part of the San Francisco Bay are moving to the southeast. And that is all being accommodated along the San Andreas Fault. And so we would call that a transform fault. It's allowing this thing to move in this direction and this to move in this direction. And so those large strike slip faults, like the San Andreas Fault, and there are many of them, by the way. It's just that the San Andreas is the most famous one. Accommodate this type of plate motion across the globe. Very important structures. So I want to take a quick moment to talk about strike slip structures that are a little more exhaustive than just simply a linear valley and deflected streams and things like this. There's some really interesting structures that we see in active faults that we really need to talk about. Things like shutter ridges. Shutter ridges are these ridges that form from the motion of the fault, which will block things off. It'll shutter off different areas. It'll deflect drainages. We'll see things like sag ponds. We'll show you an image in the next slide what that looks like. But these structures frequently jump around in the hills over time, and frequently we'll find a series of linear valleys where you'll have an older fault trace, and then the new fault, the more recent one, will jump to a better position over time. And you see this in a lot of hills. You see this in a lot of mountain ranges where you see the old fault structure that is now abandoned. It's kind of in the back, and it'll still have its own linear valley, but it won't be nearly as active. You'll have these scarps, you'll have your sag ponds, you'll have springs. Springs are a really, really strong indicator that you have an active fault happening in that area. And so I wanted to take a quick moment to show you some of these features. The first one I wanted to bring up were sag ponds and how those form along a strike slip fault. So a sag pond is due to the fact that you have imperfect movement along a strike slip fault. And when you have imperfect movement, remember this is a round earth and things don't move side by side forever. Things have to curve on a round earth. And you start having these types of problems. Strike slip fault can form something called a pull-apart basin that is bounded by normal faults. So we have strike slip faults that'll create a normal fault. How does that happen? Well, think about this block over here. These are two things that were together at one time. So this one here and this one here would have formed a big square, and then we start to pull it apart. The key here is that we have a major fault. This one here is a left lateral fault. It's moving to the left over here on that other side relative to this side over here. And it's not perfect. It's not perfectly straight. And because it has that curve, as we pull it apart, this opens up this basin, right? So this here going in this direction and this here going in this direction makes it so there's kind of a hole. There's nothing there. And that gets filled in with water and sediments and things like this. And that's called a sag pond. You can form a sag pond in this way, in these pull-apart basins. And here we see a pull-apart basin along the San Andreas Fault. Right here, it's filled in with sediment, and occasionally it fills in with water as well. And it can be an important water source for people, cattle living in the desert. The same way that you can get a pull-apart structure by having imperfect motion, you can also do the exact opposite. You can create a pop-up structure. So a pop-up structure is where you get local hills that are bounded by, in this case, reverse faults. So in this case, we have a right lateral fault, but it takes a big bend right here because, again, it's on an imperfect surface or there's some type of structure. There's a change in the geology at that locality that causes this to happen. And so it jumps from here to here. And how does it accommodate going from here to here? Well, as it's going here, it's going to start running into itself, right? This block is going in this direction. This block is coming in this. So it's crushing itself right here. And whenever you have compression, you should expect reverse faults. A great place where you see these types of structures, of course, is, again, Southern California, because you have the San Andreas Fault system. An important part of the San Andreas Fault system is the San Jacinto Fault. The San Jacinto Fault is right here. It has different segments, I should say. So there's the Claremont Fault here that moves up along Mount San Jacinto. I've done another video on the Mount San Jacinto range, so if you ever get the chance to check that out, make sure that you look for it. It's a virtual field trip. But as an aside, paralleling that is the Casa Loma Fault, which is Spanish for house on the hill. Largely because there is, in fact, a house on a pop-up structure. It's named after it. It's located right up over here. That fault is active. It comes over here. It hits this hill on this side, and then it jumps to the other side. And here we see the Clark Fault picking up on the other side. In fact, it's really the same structure. It's Here would be the Casa Loma, here's the Clark, and we have these hills forming a pop-up structure. And in fact, this is referred to as Park Hill in the Hemet, California area. Offset drainages and springs. Here we see the San Andreas Fault system moving through Desert Hot Springs, California. This is in the desert. And you got to love the desert images because the plants really stand out. You can see them. So here we see nothing but desert except right here, this lineament right here, this linear valley, that's a part of the San Andreas system. Turns out there's another fault right over here. And so we have, just like we were showing back over here, two fault traces very close by to one another. That's pretty common in these systems. And here we see one, here we see another one. And what's really interesting about this is we see all this greenery right along here and also right along here. These are springs. And these springs are feeding local desert vegetation and creating sag ponds along this area. And so the green vegetation actually shows you where the fault is located. So we have a fault located right over here. Here we have a trace of the fault. And we'll also notice that these drainages are deflected, right? They're coming in here. This is being captured here. This is being captured here. And then we have this giant drainage over here, but there's just this little canyon coming into it. This is called an underfit overfit match. So here, this is tiny wash that comes in suddenly gets really large. The reason why is this wasn't formed by this. This was formed when other larger washes were coming across the fault, and this is now just inherited this older, larger wash. And so this is an underfit overfit match that we see here. All of these are being deflected. So here we see one that's coming in, and it's still connected to this one. It's not connected over here. And here we see the springs showing that it's all matched up. Eventually, this wash here will capture this one. But that's what we mean by offset drainages and springs. The last part that I want to show you about faults, and this will be the last image on this before we go over into joints, is what fault gouge and slicken sides look like. So what does the fault actually look like when you get up on it and you put your eye on it? This is what it looks like. This is fault gouge. So this is one side of a rock. This is another side of the rock. There's a fault moving right through the middle of it, and it's just pulverized the rock in the middle. This forms a fault breccia that we're seeing in here. That's what it's referred to as a fault breccia. It just shatters these rocks. It gets pulled in there, and there could even be some ductile deformation if the rocks are deep enough. But it'll just shatter the stuff and pulverize it, this ordinarily strong rock, pulverize it in this brittle fashion. You'll see these little fractures coming off. But this shows that we have a very, very active structure. At least it was very, very powerful and very, very active at one time. Just pulverizing this rock in here. Another thing that we'll see is that you might have one side of the fault somehow exposed as it's sliding through a mountain range or something like this, and so it leaves these grooves that we call slicken sides. And so there's these slicken sides right here, and that tells us the direction of the motion of the fault as well. So this is an incredible slicken-sided face where the rocks are sliding through and leaving grooves as the fault slides along. All right, so the third type of deformation, we've talked about folds, which is ductile. We've talked about faults, which is brittle. The third one is joints. So the difference between a fault and a joint is that joints are fractures in a rock where there has been no rock movement. This is unlike a fault where there's clearly offset. Things are sliding past one another. Joints, here we actually see a bunch of joints in here. The rocks haven't moved, but there's these fractures, these very distinct fracture patterns that we see in the rocks. And these can form in many ways. They can be tectonic, or what we call tectonic joints, and we'll show you some examples of that. Those are actually the main reason why we're talking about them. They can be hydraulic joints. This is caused by pressure of fluids in the rocks being so high that it fractures the rocks. Exfoliation joints. We've talked about that when we got into erosion, and we've also talked about it under mass wasting. Unloading joints and cooling joints. We'll show you examples of those. Most occur in parallel groups called sets. So we see sets of joints. So here's a set coming in this direction. They're all going in this direction. And then there's another set going at about 90 degrees to that. We're going to get into what those are called here in a moment. So tectonic joints are the main reason why we have it in this specific lecture here. And they form as the result of the stretching of rock layers under conditions of elevated pore fluid pressure and directed tectonic stress. In other words, some type of stress coming in, usually it's compressional, but it can also be tensional. You can have it both ways. And if you look at a fold, for example, you see both tensional and compressional, and you see the way that these joints will form. So tectonic joints often reflect tectonic stresses associated with folding and faulting. And so let's look to see what kind of jointing you would expect. Brittle destruction of a rock, or brittle, I shouldn't say destruction because that's more of an erosional term, but brittle deformation of a rock that will weaken it during folding. And so when we look at these things, this is an image I found online where there was a predictive map of what type of joints that would form, these cracks, these fractures. And so we'll notice that as we get into the hinges, so here's an anticline and a syncline set, they're right next to each other, we see a tremendous amount of joints that are formed, and there might be a slight amount of displacement, I mean a few millimeters maybe at most, but effectively we're talking about fractures, right? We're not talking about faults. And so this rock here, as it comes over here into the axes of both the syncline and the anticline, the number of joints match not only the direction, right? So here we have the direction of the axial plane, which is located right here. So they follow it, and it gives us a clue about what that structure is looking like. But it also tells us something about the tensional strength or the compressional stress or the tensional stress that's happening in those rocks. So there's a lot of information we can get, and without getting into the weeds too much about how important joints are, just know that it's extremely important for engineering. Structural geologists find it extremely important for clues for what's going on in mountain ranges. And while faults are also extremely important, faults sometimes hide themselves in a way that joints can't. So we really like to look at the joints when we get a chance. Two different kinds of tectonic joints that I want to bring up in this lecture. There's more than two, but there's two principal types that I want you to know about. So tectonic joints occur as both non-systematic, in other words, there's no pattern at all, and I'll show you an example of that here in a moment, and systematic patterns. And there are two principal types of systematic sets. There's orthogonal, which is where the joints are at 90 degrees. And there's conjugate, which is where they're between 30 and 60 degrees. So they're at an angle to one another. The orthogonals are being expressed right here in this image. And this is a photograph taken in Arkansas that I found on the internet. And I think it's a great picture. This is not created by human beings. These orthogonal joints are frequently mistaken as being created by ancient civilizations. There's places that I know that has been argued that giants have created causeways and things like this in the United States, and we'll get into another place where giants have been argued. In fact, it's called the Giant's Causeway, created a different set of joints. But this is not something created by human beings. This is something that's created in nature, completely natural. So these are orthogonal joints that we see in Arkansas. And here's a different type of jointing. Here we see them at less than 90 degrees. They're at an angle between 30 and 60, right here, forming these X's. These are conjugate joints. And these also have something called parallel rock cleavage. I'm not going to get into what rock cleavage is here, but it's these parting planes that we see that's giving this rock this fabric. And so it allows this rock to break apart in parallel planes, which is roughly, if you think about this X here as being kind of orthogonal like this, and then you put an XY plane around it, or XY axis around it, these are kind of following the X axis right here. It's pretty interesting stuff. So parallel rock cleavage is definitely present here. Other common joints that we would see in nature are these unloading joints. So here we have non-systematic jointing up here. We have systematic jointing up here. Nice patterns. These are sedimentary rocks. This is a photograph from Kazakhstan. In Kazakhstan, we have these granites up here, which have non-systematic joints. There's no rhyme or reason to what's going on over here. There's exfoliation that's happening. Whereas down here in the sedimentary rocks, we find parallel sheeting joints that we see here, and this is all from unloading. And another really cool one are the cooling joints. These are basalts, but basalts are not the only igneous rock that does this. And these joints will actually form these hexagonal columns. This is a photograph. In fact, all three of these photographs are from the same place in the United States, Devil's Postpile. These are the joints that we see here, and they form these columns that extend way down, just like this. And this is formed just through cooling of, in this case, of basalts. But it turns out rhyolites will do it, andesites will do it, basalts will do it. And you get these amazing cooling joints. They're hexagonal. And again, these look like something that would be created by human beings, but they're not. There's nothing supernatural about this. This is a standard cooling joint structure that is formed even to this very day by basalt flows. And so here we see an old basalt flow here that looks like pavement, right? It looks like some human being went and did this. And this is what it looks like, the structure extending way down. So these are clear joints. These are separations that we see in the rock. It's formed by the rock through natural processes. Last part that I want to bring up, this will be the last slide for the entire show. This has been a long lecture, but it's an extremely important one, are veins and dikes. So veins and dikes are a form of joint, but they have special features. So veins and dikes, so joints filled with precipitated minerals are called veins. And so here we see some veins of gold in this case. So here we see a joint, another joint here, and the gold deposit is clearly visible in this image. So that's what we mean by a vein. A joint that is filled with solidified magma is called a dike. So here we see a joint that ripped through these rocks and magma injected itself along that joint. There doesn't appear to be a whole lot of offset, if any offset along here. In fact, if there was, it would be a fault at that point. So as a consequence, we see a dike over here, but it's effectively a magma-filled joint. So that's a lot of information, but I hope you really enjoyed it. If you have any questions, of course, make a comment. I look forward to hearing what you have to say. All the best. I'll see you in the next video. Take care.